Good morning, everyone. And welcome to lecture 3. And as of my style, I will always on Tuesday give a summary of last week. These are also the cheat sheets for you, because this is the bare minimum that you should really know. So summary of week 1. Our learning goals were to understand the scope of advanced statistical physics. And that is to describe and classify states of matter. Their collective property. And the mechanisms of their phase transitions. Driving their phase transitions. And these phase transitions arise due to the interactions between the constituents of our matter. And so that's why there's a full new class, yet again, on statistical physics, because here we're actually going to deal with the interaction that we largely ignored in statistical physics so far. But we actually need what we learned in statistical physics. So there was a recap and various cheat sheets for statistical physics and thermodynamics. And so just to give a few very important equations that will keep following us again and again. The starting point to describe a system was the partition function, which is defined as the sum over all states R e to the Boltzmann factor, here assuming the canonical ensemble. And then starting from the partition function, we can calculate the free energy as minus kVt ln of this partition function. And then from the free energy, we can derive all observables, for example, the magnetization of a system. So that would be a first order derivative of the free energy here with respect to the flat field H. And I can also define second order derivatives of the free energy, like the specific heats where X now stands for whatever property can be constant. And then this is the second order derivative with respect to temperature. Or for magnetic systems, this is stability. And these second order derivatives we also termed response function. And at last, we also talked at length about correlation functions. Function, which is defined as which measures the fluctuations or the correlation of fluctuations in a system. Here again, I'm turning to the spin system to define the strengths of fluctuation, namely the deviation from the mean spin measured at two different points in space, and the average correlation of these fluctuations, both pointing up. You would have a high correlation space. And that actually was very insightful because these fluctuations also relate to, we could show this, they also relate to the response functions. So there's a connection between the fluctuations in the system and the response, which we see from summing over the correlations. We could see that this is, in this specific case, equal to the susceptibility, where we can also write the fluctuations directly as the fluctuations in the magnetization. Let's just grab this in here. Okay. And now these derivatives are important to characterize phase transitions. And so we distinguish mainly first and second order phase transitions. And they correspond to either the first or the second derivative of the free energy having a finite discontinuity. Yeah. So in one of them is sufficient. And there was actually a follow-up question after the class where there was confusion with regards to the phase transition of the Ising model. And the confusion arose from the Ising model being similar to gases or not. And so that depends if there's an applied field or not. So in the Ising model, if you have an applied, well, what's the way? So without an applied field, it's a second order phase transition. And if you have an applied field, it's a first order phase transition. So that makes a difference in this case. And so to classify now these phase transitions that we can deduce, we introduce the concept of critical exponents. And so to this end, we rescale temperature as relative to the critical temperature at which phase transition, which I have a critical point. Now I can look at these observables like the response function or the magnetization as a function of small t, and find that there is, we'll find that there's universal, and this is just one example here, there's a universal scaling of how the stability behaves very, very close to the critical point, only described by the value of this exponent, and we will be able to classify very diverse systems into the same behavior just by their exponents being the same. And that's then called universality. So this is here now only to describe the asymptotic behavior when approaching criticality. And then we took this a little further and, for example, also derived the Rushbrook inequality, which would relate different critical exponents and show that they are dependent on each other. So that's my short summary of what you should have taken away from last week. Are there any questions before we dig into new material? Okay, so then let's dig into today. So today, the goal is give an example of field theory with the aim to sort of, again, motivate why it's going to be wonderful to learn about field theories in the course of this class, because they are a very powerful tool, as I hope you'll take away from today already. And again, the full breadth and depths will eventually follow over the upcoming weeks. And then we will start with, then we'll be done motivating what lies ahead, and we'll dig into the sort of the build step-by-step building up the story by introducing the diverse models that we're gonna play with and study to understand what drives phase transitions. Okay, and so as advertised, we start with a simple sample field theory. And we're going to talk about phonons and elasticity, thereby following Carter chapter 1.2. So any one of you taking continuum mechanics as well? Continuum mechanics. Oh, you do? Interesting. So you're in two places at the same time, right?
Oh, I did the doctor.
Ah, right. Okay, sorry. I knew this. I'm sorry. I was teaching continuum mechanics. Yes, so I'm sorry. Because like actually, stupid question, because I actually continuum mechanics runs in parallel to this class. But hey, so here's your chance that you take one bit from continuum mechanics today too, because this at least part of what we do here, as an example of field theory, this is what you would have learned in continuum mechanics too, which is basically just talking about field theories as well, but not regarding transitions. Okay, so the idea today is to illustrate the methodology by first solving a problem interacting particles and then proving field theory. Yeah, so the idea is we're going to do like brute force in really trying to solve step by step the problem of interacting particles, or like of sound waves. And you will see that this is quite cumbersome. And then the magic of folds, so for you to appreciate that if I were to write down a field theory, then I can solve exactly that same problem much faster, and I can even look at much more complicated problems with the same tools, which I wouldn't, or which I actually, in this case, like you can look into Carter chapter 1, and he gives like a page or two more of equations of how you could have tried to deal with the more complicated problem, which I'm going to spare you here, just to have you appreciate, like, look, it's really great to have this tool of a field theoretic description to understand the physics of a system we're ignoring the small length scales, which is basically what we're doing when setting up a field here. But first of all, let's go through the hardcore of, like, you know, doing all the math to, in the end, appreciate. And so that's it. We're going to look into phonons as an example. And so these are interacting particles that we consider in one dimension. And so really, to take you along, like, you know, take a note that this is only in this manner solvable here as we reduce to one dimension only. So we have to do a big sacrifice because we're only going to understand what's going on in one dimension rather than dealing with the full, I don't know, elastic material, like a wall, to consider the dynamics of phonons. So phonons are oscillations of particles relative to each other. So what we consider now in 1D is a string of particles. Sorry. And they are in a solid, so they are sort of spaced out distance a, and I will enumerate now their positions as un, their deflections un n plus 1, un minus 1, so which describes their displacement. Now, what I can do is I can write down the potential energy for these deformations. Okay. As a base potential. So this would be like a Hookean potential that is constant, and so we don't care about. And then due to these particles being connected to each other, we have an elastic constant, and as they move against each other, we have in these these springs that will be stretched, and the particles will move back. So we have like a string of springs. And so we can, in a most general form, write this as the elastic spring constant K1 over 2. Now looking at the difference of all of them individually, because they're ordered in line, I only have to look at the nearest neighbor interaction. So this would be looking at the nearest neighbor. Interaction of someone over n. But in a more general form, I can also write down next nearest neighbor interactions. That would be a different spring constant. And the next nearest neighbors would be un minus 2, un minus 2 squared. And that would be, for example, the next. Okay. And so now the way to understand, which phonons are possible is to solve for the dispersion relation and identify how base number and frequency relate to each other. So. So that's how the Patients relate to the wave number. And the way to do this is to decompose the normal modes of the system. So basically to do a Fourier transform on the lattice, which is e to the power minus I, k, and a, where a was our lattice constant, right? And then I have my deformations in Fourier space, which are consistently defined then as the inverse Fourier transform. Okay. And now making this ansatz here, I can calculate these difference terms. I will actually put the and then calculate the entire potential. So un minus 1 then becomes so what differs is the index n, right? So I have e to the power of minus k n a minus e to the power of minus chi n n minus 1 a squared. Oh, sorry, no, I didn't square it yet. Sorry for that. I was just looking at the difference here. And then we have the UK. And this we can simplify by moving out the factor minus I, k, and a, that 1 minus plus I, k, a. And now we're going to square these terms to get back to the potential. We now have the constant, and now we're putting everything in Fourier space. And now we're taking care of the square. So we have two integrals. Over dk over 2 pi and dk prime over 2 pi. We got, and I'm going to rearrange it with a minus sign. We have eka minus 1, eik prime a minus 1. And the prefactors come in as k plus k prime and a. Oops. And then we have a uk prime. And obviously also the higher order term, which I'm omitting here. And then we can use the identity that the sum over all modes minus k I k plus k prime and a is just a definition of the Dirac delta k plus k prime. So which means that if I insert, if I now take the sum over all n's here, then I would have a only a contribution for the integral for k prime equal minus k, right? But then I can also use that, then I have a u of minus k, which is actually the same as taking the complex, in this case, complex conjugate of k. because of this definition, right? It's a minus, that's the complex conjugate. That's how it comes in. Okay, so this is how we can deal with this and with this term. Let's have a look at that multiplication of the two brackets. So what we have here is that sorry, let me make this k minus k prime already a minus k. There we go. So then we have e to I k I times e to the minus I k I. So that becomes a 1 plus, oh, sorry, minus e to the I k a, another minus e to the minus I k a, and minus times minus is another plus 1. And so what we have written here, we actually know that's just the definition of the cosine, right? So that's minus 2 cosine Ka. And then we dealt with all the factors. So we can go back to our potential and rewrite as because of the Dirac delta, also one integration is already dealt with. So we just left this dk over 2 pi. And then we have here, this is the k1 term. We have a 2 minus 2 cosine of ka left. And then the higher order terms, without going into detail here, they follow in a similar manner. Cos 2 ka, and there's a bracket missing, and in principle I can go up for higher, and what's left is then the u k squared. And that's all the math that I advertised, because now we can, from this relation, we can read out the eigenfrequencies of the systems already, which give us our dispersion relation. So we can read up the eigenfrequencies as two k1 minus cos ka plus 2k2 1 minus cos 2ka plus over the mass of particles. That's already a function that I guess you wouldn't draw by hand, but you would just put in a program to plot nicely. And so if we were to do this and trust my drawing, what we have here is wk is 0 as a function of k, and it looks something like that within the extend this a tad high away. So we see that here we have a nonlinear function in general, but we also see that this range where it's actually a very handleable function, right? Because we see that also, whereas in close to the maximal distance I can have because of the finite lattice size, I have highly nonlinear behavior, but for small case, or for small wave numbers, I have a happy linear relationship between the dispersion between the frequency and the wave number. And so we see as k goes to 0, we find a linear dispersion relation where so omega for k going to 0 will then have a function of the constant that I call v times the absolute value of the wave number. And so obviously we can, from this term, we can now take the limit of taking k to 0 and really expand to solve for v, for this. And so as k1 a, sorry, one more bracket, plus 2 minus cos 2 k a, if we send k to 0, this becomes k1 plus 4 k2, plus potentially higher order interactions, which I'll summarize as a bar times a squared. And so now we find that then our v here in this ration, taking, it's just a proportional to a and so in this case, we now know really, what we know this axis and this linear behavior. So from that, we can actually also go back to our happy thermodynamic properties that we can calculate, because now we've calculated the potential, so we can calculate the energy of the system. So then the internal energy of these oscillations is constant plus, and now I'm enumerating with statistics. And since we know the eigenfrequencies, it's h squared omega over k, h squared t minus 1. And again, we can here look at the behavior at low temperature in a limiting case. Then we know that only at low temperatures, only the small wave number modes will be excited, right? And so only modes with an energy of omega h bar omega k smaller than kBt are excited. And so that means that only the k small spectral modes contributes. And so in this, taking this limit of t to 0, I can write this energy as n a so I now can take the linear relationship of no more careful in my this notation. So now I I take the linear relationship of the dispersion relation for small wave numbers that I expect are the only ones to contribute at low temperatures. So then we have here VK, and also here we only have, sorry, the H bar is missing. H bar VK over KVT minus 1. And that's now an integral that we can solve to find and so I'm aware that this is kind of a reminder of what you might have had at the last bit of statistical physics, but it's really a good example to understand, like, okay, you know, here I can calculate the phonons, I can calculate the energy, but actually what matters for me about the system is typically at moderate temperatures, at small temperatures, this linear relationship. And so I may not necessarily care about the exact value of this curve here. What I care about that it's linear, and that here the energy, and thus I know depends on t squared. Why do I care about that? Well, because this allows me again to calculate, for example, first and second order derivatives, which tell me something about my system, for example, the heat capacity, and what's the only thing that matters to me is really what's the behavior. If I increase the temperature, what will it do? And so here, just taking this limiting case, I already know what the system will do without, you know, making a statement yet about like by how much in specific numbers it will change. It's more a qualitative statement. If I forget the real prefactors, which we do have here in this case. So in conclusion, yeah, you can try to disentangle this pile of chairs and sit there. It's fine. I won't bite. Oh, okay, yeah, sure. I didn't see that one. That's hidden from my view. Okay, so in general, the dispersion relation is a complicated function. But as we go to the limit of small temperatures, we have omega versus k, and all the properties of the system, all these elastic constants, the k ones, they got actually lumped up into V, and this is a universal property of any phonons, independent of the materials chosen. And only the velocity V is interaction specific. And also the heat capacity, C of T, which is defined as dE. T scales linearly with temperature, has a universal scaling. And that is all despite, and I really want to strengthen this, we never assumed that the interactions are small, right? We never said that the case are that these elastic constants, they were small. So we have a fully interacting system that we're just looking at in a case where its relationship at low temperatures has a very simple universal behavior. So we had note, we are looking at truly is k equal going to 0 is nothing else than going to long wavelengths, which specifically means that I have a long range correlations in the oscillations. Okay. So now you can be very happy because you gained a lot of insight by going through the exercise and solving phonons. But the idea was to say, like, okay, this is what we can do, and we can only do it in 1D. But actually, what we took from the system is this behavior at low temperature where we saw all the universal properties. And there's actually a shortcut using field theory, how we can get to the same result and even have more results, because we can extend it beyond this limitation of looking at the system only in one dimension. And so this is now the phenomenological approach of fields. And so the idea of a field is that instead of dealing with looking at the positions of the individual particles that are connected to each other and oscillating, I'm gonna coarse grain on a bigger, looking at the system at a bigger length scale than the interparticle distance, the lattice spacing, and describe their dynamics as a field. So like in this case, a property that's defined continuously along space and in time. So instead of having individual deformations, un plus 1, that are numbered with an index and are therefore discrete, I will go to a field that's a u of x. And that's all behind field theories. So just, making this coarse-graining step means we're talking about field theories. And that's why, for example, everything you do in continuum mechanics is also field theories, because you just, you don't look into the individual particles in a material anymore, but you describe it as a more coarse-grained property. So the idea is, and so why is this justified here? Because we say at low temperatures, where we have the universal behavior, we have long wavelength modes where the interparticle, so the deformations that are governing the systems are actually much longer than the lattice spacing. So this lambda is going to infinity, whereas my lattice spacing A is small. And so actually, just if I want to describe this long range deformations, it's on a very different scale than the lattice spacing, and I can average over the lattice spacing. So the typical modes. Low temperature. Large wavelength. So lambda is much bigger than lattice spacing. And so I can call coarse-grained. Instead of looking at my individual particles that are A apart, we're going to look at at a continuous deformation field that I try to draw. Let me try it again. So now we turn to a deformation field. called u of x. And this u of x now has no variations on the scale of lattice spacing. And I want to emphasize that, I have no idea in which context you will come up with saying, like, I want to write down a field theory to solve my problem. And so I would really like to emphasize that you should be aware and also write it down to yourself, but also to any reader of your thesis, your paper, whatsoever. What is the assumption you're putting in? And even though it's very clear that this assumption should be verified, to you, it's very important to note it down. It's actually even very important to maybe, if you have a simulation that's investigating your system, to have a flag there that if you, vary parameters, that you check that indeed this is always true. And otherwise you have a warning that's popping up, right? Because you might easily carry it away and then end up looking at a funny phenomena of your system, which then doesn't bear any physical insight anymore, because you're validating an assumption you made up front, which is fully justified here. But just because it's so fully justified, you still shouldn't forget, right? That you made this assumption. Okay, and now the cool thing about us describing these deformations as a deformation field also means that it's much easier, because now we can also define a velocity field that would be denoted with dot u of x, which is the u of x bt, and so just writing down the kinetic energy of the system is straightforward, because that's just summing over the density and the velocity of these fields with rho now defined as the mass of our individual particles and the lattice spacing. Okay, so we can write down the kinetic energy, but we needed the potential energy, right? So now, what is the potential energy, which is now all of a sudden called not function, but function now, which is just a changed in name, because now you have a function that's a function of a function, and the function of a function is a functional, because u of x is a continuously defined function. Okay. Yeah, so we have to define this potential. And now the magic of field theories is, and as I said, in the course of, as we build the course, the field theories that will assume we can also bottom-up derive. But the beauty of field theories is that you can actually write them down top-down by just assuming general principles and symmetries about the system. And this is what I want you to take from this exercise. Not that field theories are cool, but that this top-down approach works. So we want to construct now this potential energy by general principles. And so what we want to do is that we want to write down the potential, and we know it has to be a functional of this deformations. And now we're going to consider, okay, which functional dependence is actually possible? Which ones are allowed? Are there constraints that tell us that this is okay and this is not? And so the first principle is, and all of these principles that we're going to list here, they are the same. So it's like a recipe. If you want to construct a field theory, you have the same like categories to consider, which will guide you to write down the field theory. And so the first is locality. Locality expresses that the interaction between my particles are somewhat short range. I mean, they're nearest neighbors, next nearest neighbors, maybe next nearest neighbors, but they will eventually die out and not be infinite range. And so why is this important? Because it tells me that I can make an expansion in terms of U and its derivatives, but I know that the higher order derivatives, which would capture a very long range interaction, they will be less important. So the higher the order of derivatives, the less important they should be. This is what follows from locality. Question?
Yeah, doesn't it contradict the consumer? You have a problem with phase transitions. If you have long range interaction with your system, for example, your spins, in a phase transition, your correlation length goes to infinity if you go for magnetization.
So this is just like talking about field theories in the context of phonons, which is boring from the physics side, unless you care about longitudinal and transversal wave modes, because there's no phase transitions here. So we're not there yet. This will come. The idea is really just to see an example of a simple system where we can do the meticulous one, find universal behavior, and then realize, oh, we can also find this just by very different bottom-up, top-down approach by constructing a field theory, and we arrive at the same. That's a goal of today. We're sadly not going to talk about phase transition, but that's the magic of looking at the simple system. And then we'll start when we dig with the models, and eventually, I would need to look up on the webpage. In some week, we end up with Ginzburg-Landau in theories, and then we're back to field theories. So there's quite a wait time, but this is just like, if you're still considering if you want to take the class, this is actually what lies ahead. These, just principles and so what I said with locality is, and so you're right, if you have to consider, like, what is my locality for a specific system, but here we can rightfully make the assumption that the interaction between particles are short-ranged, and correlations are not the same as interactions, right?
Because
No. Correlations is like, okay, what's a cool example? There are all these funny correlations. So a correlation, gosh, doesn't come to mind. But you can calculate, I don't know, the amount of cows in a country and what people vote, right? And you find correlations, which doesn't mean there's any causality between them, right? Okay. So if fluctuations are correlated, doesn't mean that the constituents that are making up your matter are interacting on these long range. It just means that they're doing the same thing, but that's not because the interaction is long ranged. These are two different things.
Okay, because something that I remembered from reading, in a system where your correlation length diverges goes to infinity, in a spin system, in a metal, you have your magnetization.
Yeah.
You order
yeah, but it's the same idea of, like, if we all touch hands, we don't have to do this, no. But if you all touch hands and I'm interacting with my nearest neighbors and I'm shaking their arm, then if he shakes the next arm, then we can have like a collective motion, all of us together, despite the fact that we're just interacting on a local range, right?
Yeah, okay.
Yeah. It's like, take a fish of schools, like a school of fish, sorry, a school of fish. A school of fish, and the way the fish are interacting with each other is just by nearest neighbors, right? So they sense where's my neighbor, and but if everybody sort of aligns to some extent with their neighbor, the whole school of fish will go into a swirl without there being an orchestrating interaction between all fish to say, like, let's go swirl. You've seen these, right? Yeah.
Yeah. Okay, to sum it up, you can have only next nearest neighbor interactions, but at the same time system-wide changes.
Yes. Short range little, i.e., oops. Okay, so we start by assuming that our functional looks like some integral of some function phi, and there might be u of x and du of dx and so on, but eventually I can ignore higher order terms. There are the constraints. So, for example, in this case, we have translational symmetry, which means that the physics is the same if I look at particle un or un plus 5, right? And so, and in the field theoretic context, that would mean that this function phi of u of x plus c has to be the same function as phi of u of x. And so this has to be true now for any c. And that tells me that there cannot be any direct dependence on u of x. And so now we change our assumption and say, okay, then our phi has to be a function of du dx, du squared, dx squared, and so on, only. Then we put up another constraint, which is the stability. Yeah.
Question. Why am I moving my my displacement field with C? Normally, when I talk about translational symmetry, I would the argument of the displacement field. So I would ask if the system that is that has displacements, it looks the same if I move it from like I don't know.
It's sorry, it's a I guess it's just me, like I don't trust my notes to the extent. Yeah. The bracket was on the wrong.
Oh, okay.
Yeah, but it has to be, but it's not true. Like I can also like make the other statement of saying like C needs to be any functional, right? You know, I displace, I'm looking at any other, no, it's not true. So if I have u of x plus c, and look, there's another bracket missing, then independent of how I'm translating it, it should be the same. Yeah, and that it gives the same conclusion, right? So that wasn't.
That doesn't give the same conclusion. Like, okay,
So this has to be true for any C.
Yeah, so the integral of some function of u of C, if the integral is over the whole space, doesn't change when we translate x, you know, somewhere. I think yes.
But I could have, for example, also sorry, whoops. Like if I have I have u in linear combinations, with other functions, then it would make a difference, right? So I can't have u du dx. You agree on that? With this symmetry. I think that's the easy example. So if I have u shifted in x, but I'm multiplying with the derivatives, then I will get a different result if I evaluated at different values of x, because I shifted my x.
Yeah, but you know, if we integrate, we can always change the variables to x from x to x plus c, and then the integral stays the same. No?
yeah.
But we're only integrating within, sorry, we're still only integrating within the Briand zone, no?
there a Brillouin zone in a continuous mechanical case because I'm letting A go to 0, so K over A goes to infinity, so my Brillouin zone goes over the whole momentum.
Base.
Mm.
No, it's not like I'm not sending A to 0. A is still finite.
Oh,
I'm
okay.
looking at deformations that are bigger than A.
Mhm.
This is two different things.
Okay, yeah.
So I don't send A to 0. So I can't, I'm just looking at dynamics on a larger space. So I still have a cutoff on the Brillouin zone. There's a range within which I can integrate.
But then how does that, how does the transition symmetry demand only the dependence in derivatives from special derivatives? How do we get from this?
So
From this line to the second line?
it actually it could so the I would need to look it up if there's if this is the stage. I think this is how I'm pretty sure I could this correctly. But actually the linear dependence also follows from the stability argument, because what stability requires you is that there's an equilibrium state from which we're oscillating or from which we're deviating off, and to have a stable state means that there can also implies that there cannot be a linear dependence on you, because that would mean that I can have add a finite deformation and thereby change my equilibrium state. And I can't. I say there's one defined equilibrium state of my system, and I'm just looking at the variations around. And that's I would need to look it up, but it could be that the translation argument only don't allows you to have combinations of U and derivatives, which would break that one because of the Brillouin zone, and the stability tells you then that there's also not the linear term, the single linear term in U, because we only want to have fluctuations around equilibrium configuration, which again I have no U of X dependence. And I even learned something more about my system, because it also tells me that the quadratic part has to be positive. Like if you think about a potential, you want to have a potential that moves you back to your equilibrium state. So rather than like having a divergence that the potential makes your particles fall apart, it has to be bounding and move the particles back. So we also learn that the quadratic part is positive. Okay. And so the approach is to start with the most general potential resulting from those general principles. And that would be V of U, X, that would be du dx. There's another assumption I'm just going to write down. And in principle, I can also have these mixed terms here. U dx squared, d squared u, and so on. So there's one more assumption that I'm putting in here, which is that it shouldn't matter for the particles if they're collectively moving to the right or collectively moving to the left. And so that's why also the linear derivative has a square, because the sign of the deformation doesn't make a difference for the energetic cost of this deformation. No deformation. Same energy. Which is obviously only true for a regular lattice. Okay. And now we can start with this potential and we go back to like, let's calculate the dispersion relation. And we do so in the same fashion of taking the Fourier transform, which though is a little easier in the sense of, because right away back down, we have k over 2, k squared plus L over 2, k to the 4. U over k squared. And then the interaction terms, yes?
Where do the other terms come from in the most general potential?
So
Like the
I
second
can,
derivative,
so far we only extruded linear terms. And I can just write down every combination of derivatives. I know that this one, so that the linear derivatives, they have to come with a square. And also the, you know, it's true also for all higher derivative, but I can write down all terms. In principle, this is like an infinitely long list that I can write down.
okay.
And then the only thing that saves me from dealing with all of them is this thing, which tells me like, oh, by the way, yes, I can write down the 5th order derivative, but I don't care because the interaction is not that long range that particle here with 20 down the road is actually, you know, interacting actively. So there's a short range interaction, so I can actually cut off higher order terms. But still, even if I were to take all of them along, just writing down the Fourier transform of these terms is, and sorry, there's a term missing, right? Is still much more handy than doing that for the actual displacement fields, looking at deformation fields, UN minus UN plus, and so on. And so on.
Okay, thank you. And,
Sure.
and for example, the prefactor L R.
I just make them up. So that's,
You just do it.
yeah, that you now discovered the fail.
Yeah,
So
okay.
here, thank you, you discovered the fail of field theories, which is when I basically cook, right? You know, I take my ingredients and I cook up this potential. I know of how it should look like, but these prefactors have no direct physical connection.
Okay.
So I can, I'm very happy if I find something in my system like, oh, you know, it has to be stable. So I know that the quadratic part has a positive prefactor. So I can say something about the sign of the prefactor, and that's already an achievement, right? But I can't say anything of the magnitude. So what we lose in the end is that the parameters that are governing the dynamics. So we get the same qualitative dynamics in a much cheaper and much broader context. But what we lose is that the prefactor that tell us how of the dispersion relation, our velocities, for example, the velocity does not anymore connect to any material property. So here in this context, where is my velocity? Yeah, right. I could have daydreamed that you know, I know the mass of my particles, I know the lattice spacing, I can, yeah, actually, can I calculate the velocity? I mean, do I really know the spring constants? We typically don't, right?
for lots of materials, like it's going to be very hard to make a statement about what are these Ks, right? So I kind of have a feeling I know my velocity, which is governing my dispersion relationship, but also, for example, you know, my specific heat. That's the only parameter that pops up here, right? But in the end, I actually don't know it for the materials anyway. And so I'm throwing out this here. I'm throwing this out by just putting down a number where I'm not claiming that this has a specific functional relationship to the lattice spacing or an elastic constant that I don't know about anyway. Yeah. Yeah, another question.
How do you approximate your p-factors in a simulation? If you have a simulation and you have a certain material or a certain model, you need to approximate something to fit in a certain range. You have your K half and you have L half. So how do you do that?
So what you should do, in my opinion, is you screen the dynamics of your system by varying these parameters over plus minus sign orders of magnitude, so they have an idea of what capabilities your system is, what behaviors your system is capable of, and then you either have a specific phenomenon you want to describe on a theoretical level, or you have experimental data, and then you use this screen to then go into this regime where you have something either from the qualitative behavior or from actual, like something that you measured, which would be then specific heats to fit it. And you have fit parameters. So they're free fit parameters, which honestly, for the dispersion relation, the velocity is also a fit parameter yet, as I said, because we don't know really the elastic constants. Right? My second term. Yeah, and then these mixed terms, obviously they're a little more complicated. So that's why I hope you convince you that we don't want to go too much into the higher order terms, but just to give you a flavor of how they look like. So this is now looking at this term. K1, K2. Oops. View of K1, K2, view of minus K1. Yeah, third order term. And now we're going to simplify it quickly and say we are really interested in the dynamics as K goes to 0, where it's safe to ignore the higher order terms. Because the higher order terms obviously have higher orders of K contributing, right? So this is K squared, K to the 4, K to the 4 as well, and so on. And so the simplest model in this case is we consider now small deformations, neglect higher order in U. So we can write down the one-dimensional theory, where now Hamiltonian is summing over the kinetic energy, right? That we was easy to write down. And I'm going to actually abbreviate this prefactor here as V squared. Oops. U dx squared. So just take into account the lowest order term, the K squared term. And so that would be the Hamiltonian of an elastic string with, and in this case, we actually know this,
material specific constants rho and b that we know is k over 1. So what we gain here, we can easily read off this equation. The universal behavior is temperature goes to 0, and the dispersion relation from the Fourier modes. Right, it's basically already written down on this equation on this line. And what we lose is what we just discussed. We don't really have a microscopic mapping of the velocities anymore, because the k, what is the k here, we lack how this translates to the picture of the elastic string modulus k1 and the lattice spacing. Right. But here it comes. The big gain is we can generalize to arbitrary dimension. And this is where the big business starts. The big gain, we can generalize. Say we consider an isotropic material. Now our U becomes a U vector field in 3 dimensions, which I'll denote with U alpha, alpha being the index that now goes over the 3 space dimensions. And then here in this, for this isotropic material in 3 dimensions, I can introduce a strain field. This is just about concepts. I don't expect you to do continuum mechanics in this class. So the strain field that we introduce here, and now you've seen it as well, or you'll revisit it, is then defined as the derivative of the, say, x, like iterating over all components and taking their derivative with all other components in the field. So this is a 3-dimensional tensor. But the gain is I can write this down in a shorthand form. And for such a 3-dimensional deformation field now, I know that the symmetries of the system require invariance under rotation translation. And so taking this, I can write down the Hamiltonian of the system as, and here I'm using Einstein notation again, this being the sum over all 3 space dimensions, rho du alpha dt du alpha dt plus, and now here summing over these derivatives, and So this is just an example that I can write this from the principles. I can ad hoc write down such a Hamiltonian for a three-dimensional material. And if we take this Hamiltonian as a given, you don't really have to fully penetrate how it comes about. But the cool thing is that we see the symmetries popping up in the system. So we see the rotational invariance in Fourier basis, which is which we can, so this is tanya, okay, squared, yeah, and then here we have mu over 2 a k squared u over k squared, mu over, sorry, plus lambda. And this is k squared. And so these are then all rotational invariant. And so just by sort of starting from the symmetries to set up the Hamiltonian going into Fourier space, we again, in Fourier space, we can directly read off the dispersion relationships. So we can easily read the modes. So for the wave vector being in parallel to the deformation field, we have both of them, both of these terms contributing, right? This gives because they are in parallel, and then they have a velocity that's given by 2 mu plus lambda over rho. But if the deformation is perpendicular to the wave number, then we have this contribution being 0, and we have the transversal mode of mu over rho. So here is our longitudinal modes. And this is a transversal mode. And as before, we can also readily write down the internal energy. LD, that's the volume. And dvk. And again, now writing, since we do have the dispersion relationships, we sum over both of these contributions. So we have h bar VL k over E h bar VL k AVT minus 1 and h bar VT k plus, sorry, E h bar VT k up over Okay, so we know the energy. And again, we can look at the behavior as we take temperature to 0. And so as we take T to 0, we see that, okay, there's some prefactor that depends on the exact value of VL and VT. But what is really dominating the scaling is L to the D, KBT, D plus 1. And so we can readily read off the specific heat as t to the power d for t going to 0. And again, there's only t to the d. There's no VL, VT, parameter popping up in the scaling behavior. And so we again found a universal property. So we have here a universal scaling. And this exponent really depends on dimension, and the assumption that we made here, obviously the range of interaction. And so what we did here now is really show an example of side by side in a simple system, which sadly, look, there's no phase transition. So these complex interactions that we have here between photons just being elastically, particles being elastically connected with each other and sort of oscillating together, there's no phase transition, so we need more complex. So we need missing. So we need more complex interactions to actually gain these phase transitions. But the whole purpose of going through this exercise was not to dig into phase transitions, but just to show side by side, this is what I can do, calculating a simple model in a limited range, namely one dimension. And this is what I can do when we dig into field theories. That said, this is the end of the motivations of why it's cool to learn advanced statistical physics. And now, from now on, we're going to dig into the models, and then we're going to do, like, what can we do directly calculating in one dimensions, which is our fate. This is where you can explicitly solve systems. And then we'll realize that the one-dimensional systems are the less interesting one. They're kind of boring phase transition-wise again. And then we work ourselves up in finding the different tools to say something about the more more interesting dimensions as we work as we expand our tool sets from direct evaluations to series expansions to field theories, and then to the randomization group. And with that, I'm happy to take any further questions. And I thank you for your attention for today. Thank you.